Beneath a farmhouse on the northern Korean peninsula, a fire burns 2 hours every morning. By the time the family wakes, it is already out. But the floor is warm, and it stays warm through the afternoon, through dinner, through the night, while temperatures outside fall to -20 degrees Celsius. No boiler, no thermostat, no electricity, no moving parts, just stone, channels beneath the floor, and a single morning fire. Modern radiant floor heating costs $10 to $20 per square foot to install. It requires a gas boiler or electric system tied to a grid that fails in winter storms, and a contractor when something breaks. The Korean system needs none of that. No refrigerant, no pump, no electronics. It is stone and geometry. It is called Ondol. And in most Western countries, building one in a residential home is effectively illegal under current building code. What is this floor? How does stone hold heat for 12 hours after the fire dies? And why, if it genuinely works, can you not build one today? The answer begins over 2,000 years ago, in a climate that gave people little choice. The northern Korean peninsula in winter is brutal. Temperatures hold below freezing for months. Timber was scarce on the exposed plateaus. Families needed a heating system that could extract maximum warmth from minimum fuel and hold it through a full night. The Ondol did not emerge from philosophy. It emerged from the calculation of how to stay alive with what was locally available. The design is exact. A firebox, the agunji, sits at one end of the building, often in the kitchen where cooking fires already burn. Beneath the floor runs a network of low stone channels called gorai. Hot combustion gases travel through those channels, pressing against the stone slab above before escaping through a chimney at the far end of the room. The floor absorbs the heat. When the fire dies, the slab is fully charged. Residents sleep directly on that surface, drawing warmth upward through the body. Interior temperatures stayed above 18 degrees Celsius through winters that reached -20 degrees Celsius outside. This was not comfort. It was survival infrastructure. A failed Ondol in a Korean winter was a life-threatening failure. The system was refined over centuries because the consequences of error were immediate. The Romans reached the same physics from a different direction. In their bathhouses and villas, engineers raised stone tiles on short pillars called pilae, creating a hollow plenum beneath the floor. A furnace, the prefernium, pushed hot air through that chamber. The tiles absorbed the heat and radiated it evenly upward. In some buildings, hollow wall tiles called tubuli channeled heat up through the walls as well. Roman engineers knew that chimney placement determined whether air traveled the full plenum or short-circuited and escaped before heating the floor. They were solving structural physics, not following tradition. From a Korean farm firebox to a Roman civic bathhouse heating hundreds of people, the same principle, twice. Thermal mass is one of the most effective heating strategies ever applied to a building. It runs on almost nothing except correct geometry and dense material. In recent decades, off-grid builders in Montana, rural Scandinavia, and parts of Eastern Europe confronted the same problem. Propane and electric heating in remote areas is expensive. Grid outages in winter are dangerous. Modern radiant floor systems require functioning infrastructure and costly service calls. Some of these builders had studied Korean Ondol. Others had built rocket mass heaters, a modern masonry combustion design that burns small-diameter wood at very high efficiency. A few recognized the connection. The same thermal mass principle could extend into a subfloor channel network, reviving the Ondol structure with contemporary geometry. Homes built on this principle, using rammed earth or fieldstone slabs over low masonry channels, have maintained interior temperatures between 19 and 22 degrees Celsius through multi-day cold snaps on a single 2-hour fire each morning, burning 3 to 5 kilograms of wood. These builders were not geniuses. They read historical documents, understood the physics, and sourced materials from a gravel yard and a salvage yard. Here is how it works. Stone stores heat. Dense stone has high specific heat capacity. It absorbs a large quantity of thermal energy before its surface temperature rises and releases that energy slowly. The floor becomes a battery. The fire charges it. When the fire goes out, the battery keeps discharging into the room. But the material alone is not the trick. The channel geometry is where the design becomes precise. The Gorade channels are low and wide. This forces hot gases to slow down, spread across maximum stone surface area, and transfer as much heat as possible into the slab before escaping. Every meter of channel contact matters. A short channel loses heat up the flue before the stone is fully charged. A long, correctly proportioned channel uses nearly all of it. The chimney is the engine. Hot gases move horizontally through the floor channels because the chimney at the far end creates a pressure differential, a passive draft that pulls combustion gases across the full length of the floor. The fire and chimney form a pump with no moving parts. Place the chimney exit in the wrong position and gases short-circuit, escaping before heating most of the floor. The entire performance of the system depends on that one exit point. The slab must seal the channels completely. Any gap leaks heat down into dead space instead of upward into the room. Traditional builders sealed joints with lime mortar, firm enough to hold, but not permanently rigid. After the fire dies, conduction continues for hours. The floor surface reaches between 28 and 35 degrees Celsius, warm underfoot, not uncomfortable. That warmth rises through the body of anyone sitting or lying on it. The room holds temperature through the night with nothing running. Gravity and mass do the remaining work. Traditional Korean Ondol homes maintained interior temperatures of 18 to 24 degrees Celsius in minus 10 degrees conditions, using 4 to 6 kilograms of biomass per day. The average European gas-heated home consumes 15 to 20,000 kilowatt-hours per year for heating. A well-insulated Ondol-style building runs on a fraction of that, in wood, storable locally, independent of any supply chain. The quality of that warmth is different. Heat rises from the floor, not a vent. No pump cycles on at 2 in the morning. No boiler ignites in the hallway. The room warms slowly and holds evenly. No forced air circulates dust. In an earthen slab, the first heat of the day releases a faint mineral smell, like stone after rain. When something eventually needs repair, the fix is mortar and a set of hands. So why is this not the standard? The honest answer? It does not work everywhere. It performs best in well-insulated buildings where the envelope loses heat slowly. In a poorly sealed house, the floor charges and the room leaks that energy faster than the slab can replace it. It cannot be easily retrofitted beneath an existing poured concrete floor. Channel length and slab mass must be sized for the room. Undersized systems cool too fast, while oversized ones respond slowly. The firebox needs a proper flue to prevent smoke from backing into the living space. Biomass requires storage, which makes this impractical in a dense urban apartment. These are real limits, but they do not explain why the system barely exists in any modern building conversation. The deeper reason is that modern construction rewards a specific kind of solution. Building codes in most Western jurisdictions require solid fuel appliances to carry factory certification with tested emission ratings and a model number. A masonry channel built on-site has none of that. An inspector cannot tick the box. An insurer cannot assign a standard risk category. Contractors are trained on boiler systems, electric radiant mats, and forced air HVAC. Masonry heat is a dead trade in most of these countries. Developers choose the cheapest system to install because tenants pay the utility bills. Boiler manufacturers and electric heating suppliers have nothing to sell once the stone floor is built. It needs no service appointment, no refrigerant recharge, no replacement cycle. It lasts the life of the building, generating no recurring revenue for anyone. This is not a conspiracy. Nobody suppressed Ondol at a meeting. It is the accumulated weight of every code category, contractor certification, and market incentive pointing away from systems that are durable, local, passive, and impossible to monetize through parts and service. The principle can be recovered. Building from scratch in a cold climate, use dense stone, flagstone, granite, fieldstone, or rammed earth. Lightweight blocks will not hold heat. Channels need to run 15 to 25 centimeters in height across the full room length. The slab above needs at least 8 to 12 centimeters of thickness. A rocket mass heater can serve as the firebox, efficient, low emission, and permitted under experimental exemptions in some jurisdictions. Natural building networks and rocket stove communities have open-source plans already tested in real homes. Address the building envelope first. Heating a leaky structure with a stone floor is heating the outdoors. The Ondol and the Roman hypocaust were not primitive systems. They were sophisticated thermal engineering, built from local materials, refined under survival conditions, capable of warming a home on almost nothing. What replaced them was not necessarily better. It was easier to package, certify, and sell. This pattern repeats across every domain: cooling, food storage, water, structure. Solutions that worked for centuries disappeared, not because they failed, but because they could not be given a model number and billed through a service contract. The floor beneath your feet could be doing this work right now. That it is not an accident of progress. The same thermal mass principle that heats a floor goes underground in the next video, into the Roman earth cellar and the Korean kimchi pit. Chambers where stable ground temperature preserves food year-round with no electricity, no refrigerant, and nothing moving at all.